So our first speaker today is Yujun Wang. He's going to be talking about signatures of Efimov, the Efimov effect in hot three-body collisions, and you might recognize his opening figure here as the figure from the cover of our workshop booklet. So,
yeah, thanks, Seth. Thanks for the organizers to invite me here to talk about the signature of the Efimov effect in hot three-body collisions. I would also like to thank the organizer to use this figure that shows the connection between the zero energy Efimov feature and the finite Efimov energy features on the booklet for the workshop. So this is the outline of my talk. First, I will give a brief introduction to the Efimov effect and also the observation of the Efimov state in ultra-cold atoms. Then I will move to the Efimov physics beyond ultra-cold regime, where I will first show the Efimov characters in the finite energy three-body scattering wave functions. Next, I will show the finite energy Efimov features, specifically in three-body recombination. Then I will discuss the contribution from higher partial waves that can affect the three-body observable. Finally, I'll give a summary and some outlook. So what is the Efimov effect? So as many of you have already known, in 1970, the nuclear physicist Vitaly Efimov predicted that for three particles with isotropic and short-range interactions, they can form an infinite number of three-body bound states with energies follow this geometric scaling when the scattering length is infinite, or when the binding energy equivalently when the binding energy of two particles is exactly zero. So here I'm showing the sketch of the three-body energy spectrum as a function of the inverse scatter length. As you can see, as the scatter length increases, three-body bound states can form either from a three-body continua when the scatter length is negative, or from the atom-molecule breakup continua when the scatter length is positive. There are many interesting characters of the Efimov states. For instance, when the scatter length is negative, the Efimov states are Borromean states, which is shown as indicated by this small logo. It implies that when any one of the particles is removed from an Efimov state, the whole state will break up. Now, at unitarity where the scatter length is infinite, it's pretty bizarre that there are infinite number of three-body bound states with only short-range interactions. And finally, the most counterintuitive character of the Efimov effect occurs for positive scatter length, where as you increase the strength of the underlying interaction between particles so that the scatter length between two particles becomes smaller in this direction, you get less number of three-body bound states. This is contradictory to our normal expectation, where we would expect stronger interaction will provide more binding to the system, in contradiction to this scenario. So how do we understand this bizarre effect? For this purpose, I would like to introduce the theoretical tool we use to study the Efimov physics, the hyperspherical coordinates. In a few-body system, if the interaction between particles do not break the overall translational symmetry, the center of mass motion can separate from the relative motion. Now, there are many ways to write the coordinate system to make this separation. One possibility is use the Jacobi vectors, which can be obtained by connecting the center of mass of the subsystems. For three particles, only two of the vectors will be relevant here. Now, the hyperradius is defined by the sum of the squares of the Jacobi vectors. The rest degrees of freedom in this three-body system is represented by the hyperangles. The definition for the hyperangles can vary a lot depending on a specific choice in applications. So they can define as spatial angles, or by the relative size of the Jacobi vectors, or moment inertia, or even the geometry of the system. Now, one biggest advantage of the hyperspherical coordinate is that there's only one coordinate, the hyperradius, that can go to infinite when the system breaks, which is very convenient in treating three-body scattering problem or three-body physics, studying three-body physics with long-range scaling behavior. Although it's powerful, it still have difficulty in solving this three-body Schrodinger equation in this coordinates system with large degrees of freedom. So the trick is to use proper expansion for the total three-body wave function. Now, by noticing the conservation of the total angular momentum, we can use the eigenfunctions for the total angular momentum as part of the expansion basis. Now, to better represent the geometry of three particles, we use the eigenfunctions of the Hamiltonian, three-body Hamiltonian for fixed hyperradius as the rest part of the basis. Then, by using this expansion, the six-dimensional three-body Schrodinger equation can be casted in a coupled hyperradial equations, where in this case, we can use all the knowledge and technology we have developed for solving coupled systems. In this representation, the hyperspherical potential, adiabatic hyperspherical potential U, which can be obtained by solving this adiabatic equation, plays a central role because this potential largely determines the scaling behavior for the whole three-body spectrum. So with this tool, how do we understand the Efimov physics or Efimov effect? Now here I'm showing a set of hyperspherical potentials for three identical bosons. People have found out that when hyperradius is much smaller the size of scatter length, there's a potential right below the three-body breakup threshold that behaves like an attractive 1R square long-range form. Now it turns out the coupling between the different channels is relatively weak, so that we can use a single-channel approximation and determine three-body spectrum. The solution to this to the hyperradial equation with this potential can be analytically written down simply with a linear combination of Bessel functions with imaginary order. However, as has been pointed out decades ago by Morse and Feshbach, the solution for this potential is yield-behaved. If the potential, this attractive 1R square potential, extend to 0 hyperradius, the corresponding wave function, the hyperradial wave function will oscillate infinitely fast near the origin, and there will be no lower bound for the three-body energy. And this is called the Thomas collapse. Unfortunately, in realistic systems, there's always some short-range interactions that makes this effective potential repulsive at small distance. The position of this repulsive wall determines the ground Efimov state energy, and in turn determines the so-called three-body parameter. So the energy spectrum for this potential with a repulsive barrier is exactly the same as Efimov energy spectrum, which is a geometric series. So the existence of this long-range potential is the origin of the Efimov effect. So we now know where the Efimov they come from, but the question now is that what brings in this long-range potential with only short-range interactions? To get some insight, it's better to go to a system with two identical bosons and one light particle. In this system, the motion of the light particle can be treated by Bohr-Oppenheimer approximation, and the hyperspherical potential for this system is approximately given by the Bohr-Oppenheimer potential. So it turns out people have found when the distance between the two heavy particles is much smaller, the scatter length between the heteronuclear pair, the effective Bohr-Oppenheimer potential mediated by this light particle also have this attractive 1R square behavior. which is the correspondence for this attractive one-word-square behavior for identical bosons. So also this long-range attractive one-word-square behavior in this system is in the form of the exchange energy for the light particle between the two heavy particles. Therefore, the Efimov effect can also be understood by the enhanced exchange energy from long-range correlations that brings in by the large scattering length. So now we understand the Efimov, how the Efimov effect comes in. The question now is how do we observe these states? Now, it turns out the formation of Efimov states can strongly affect the three-body scattering process in ultra-cold atoms. So when the scattering is negative, when the Efimov states are formed from the three-body continua, resonant peak will appear in three-body recombination rate. Now, for positive scattering lengths, between the formation of two Efimov states, there will be one interference minimum related to the formation of Efimov states in three-body recombination rate. Also, for positive scattering lengths, at the position where the Efimov state is formed, there's a resonant peak shown in the vibrational relaxation for the Feshbach molecule. So there's one common feature for all these three-body scattering observable is the log-separated features or log-periodic features as a function of the scattering length, which can be traced back to the geometric scaling of the Efimov binding energy. So in general, these log-periodic features can be used as smoking gun for detecting Efimov states in the three-body system. Now, the first experimental observation of Efimov states were made in Innsbruck in 2006, where they used cesium atoms and tuned the scattering length near a Feshbach resonance. They observe a resonant peak at negative scattering length, also an interference minimum for positive scattering length. They have also shown that when the temperature is increased, the strength of the Efimov feature become weaker. So this indicates that these kind of Efimov features in three-body scattering observable should be observed in the ultra-cold limit. But how cold is cold? It turns out to observing these Efimov features, the temperature or collisional energy for three-body system should be lower than a threshold energy, which is approximately given by the binding energy of Feshbach molecule. Now, to observe the first Efimov feature, depending on the mass of the atomic species, the temperature is typically ranged from nanokelvin to microkelvin. Now, after the first experimental observation, there has been many experimental observations in ultra-cold atoms for Efimov states, ranging from including observation in three-body recombination, vibrational relaxation of Feshbach molecule, and even the microwave association of Efimov states. But there still remains this question: does the Efimov effect only show up in the ultra-cold regime? So I will address this question in the next session. So let's consider such a scenario where the scattering energy of three particles is much higher than the threshold energy, but still much smaller than the scale of the short-range cutoff energy. Now, we can apply a WKB analysis by looking at the correction to the WKB approximation for different hyperradius. What we found is that there's one quantum region where the correction is non-negligible, and there's a classical type of regime where the correction is almost zero. So it's clear that in this quantum region, this three-body scattering wave function bears some character of the Efimov states or Efimov effect. As the scattering energy changes from the threshold energy to the short-range energy scale, this boundary scans through the whole Efimov potential from R0 to scatter length. So the question now here is that will the character in the scattering wave function be manifested in the three-body scattering, or scattering observables specifically? So to answer this question, let's look at how three-body recombination occur in these systems. And for positive scatter lengths, here I'm showing the two hyperspherical potentials that are relevant to the three-body recombination. Now, in the lower channel, in the Efimov region, the potential is a 1 square attractive behavior. Asymptotically, this channel goes to the atom-molecule threshold. The upper channel represents the three free particles. It is both repulsive in the Efimov region and asymptotic region, although with different coefficients. And numerically, we have confirmed that the coupling between these two channels are relatively weak, except in the region that connects the Efimov and asymptotic region. In this case, we can write down the analytical solution for this for the hyperradial equation for these potentials in the Efimov region and the asymptotic region independently, and by assuming some simple form of coupling in this intermediate region, we can derive a three-body recombination rate in analytical form, which is featured by inverse power law scaling with a wave number, or square of the energy, and also a log periodic dependence on the energy. To get more insight into this expression, I would like to use a pathway analysis for three-body recombination to see how things happen. So to make things clear, I'm using different colors to represent the two potentials, and also where the three particles stays, in which channels three particles stays during the pass. So there are two major pathways for recombination at positive scatter length. In the first pathway, three particles comes in and pass through the intermediate region in the first time, then get reflected by the upper potential at smaller distance. Now when they return to the intermediate region for the second time, they make a transition to the lower channel, and this gives the recombination in the first pathway. In the second pathway, three particles comes in and make transition at the first time when they pass through this intermediate region in the lower channel. Then, in the lower channel, they still continue to move in and accumulate much more phases in this potential, and get reflected back in the short-range region. Then continue stay in the lower channel for recombination. So by adding the amplitude for these two pathways coherently, we can get essentially the same expression for three-body recombination rate at this one, for this energy range. For the energy range that is much higher than this threshold energy, but much smaller than this short-range energy scale. So for negative scatter length, things are a little different. Because the absence of the Feshbach molecule in this case, the Efimov potential can only asymptotically connect to the lowest three-body continua channel. So for recombination, three particles comes in this channel and stay in this channel until they reach the short-range region where they can recombine into the deeply bound atom molecule thresholds, channels. Sorry. In the first look, it seems like the Efimov potential here plays no role in three-body recombination. However, if you remember what I just mentioned, in the quantum region, where the potential, Efimov potential, the depth of the Efimov potential is much higher than the collisional energy, there's so-called quantum reflection, which means that when three particles comes in, part of the amplitude will be reflected back before they can get into the short-range region. The amount of this reflection depends on the collisional energy. So in principle, the character of Efimov potential should be retained partially in the three-body scattering energy, or in the three-body scattering wave function, and therefore in the three-body recombination rate. So similar to the positive scattering length case, we can here also write down the solution analytically in the Efimov region and the asymptotic region independently, and allow the recombination at small distance by introducing complex absorbing potential. By doing this, we were able to derive an analytical expression for three-body recombination rate at negative scattering length, which is also featured by an inverse power law dependence on the energy or wave number, and also a log periodic dependence on the energy. For comparison, here I'm also giving the expressions for three-body recombination rate at low energies. So in both cases, we can see the character or characteristic Efimov features as the log periodic dependence either on the wave number or the scattering length. So because of this, now we should be able to observe the Efimov features in both the ultra-cold regime and finite energy regime. So here I'm showing more details for the connections between the zero energy and the finite energy Efimov features for both positive and negative scattering length. Now in both figures, the diagonal line gives the threshold energy that is determined by the scattering length and the mass. Now for positive scattering length, below this threshold energy, now we can see the scattering length dependent oscillations. Now above this threshold energy, we can see the energy dependent oscillations as signature of the Efimov effect. Now for negative scattering length, below this threshold energy, we see the resonant peaks, log-separated, log-periodic resonant peaks as a formation of the Efimov states. Above this energy, things are a little different. Instead of resonant peaks, we see relatively weak log-periodic oscillations, but also as signature of Efimov effect. So from this figure, we can see that the zero energy Efimov feature has 1-to-1 correspondence with the finite energy feature in both cases. So this indicates that by counting the number of finite energy features, finite energy Efimov features, we can directly know the number of Efimov states in a system without tuning the scattering length or interaction. So this is pretty convenient for looking at Efimov states or studying Efimov physics in systems where the interaction cannot be easily tuned. For instance, one most important example is in nuclear systems. In a nuclear system, the relevant energy scale for the finite energy Efimov features can range from keV to MeV, which is about 16 orders of magnitude higher than ultra-cold atoms. Oh, sorry. So there's one difficulty, however, to observe the finite energy Efimov features, which is the large separation between the features in energy scale. For identical bosons, the separation here is a factor of about 500 for consecutive finite energy Efimov features. Now, to reduce the separation between Efimov features, we can go to systems with heteronuclear pairs. Now, here I'm showing the scaled three-body recombination rate for heteronuclear systems by changing with different mass ratios and also identical particle symmetries. Now, by changing identical particle symmetry and also mass ratio of the third atom, the separation between the Efimov features can range from over 1 million for 2 cesium in same spin state and another cesium atom in different spin state to about factor of 24, which is for 2 cesium atoms and 1 lithium atom. Now, for positive scattering length case, the modulation of these Efimov oscillations increases when the separation between the features becomes smaller. Now, however, for negative scatter lengths, the modulation of the oscillation becomes smaller when the separation between the features becomes smaller. So from these pictures, it seems like it's better to look at the finite energy Efimov features at positive scatter lengths. However, these results are both for the lowest partial wave, the j = 0 orbital angular momentum. One thing I left out up to now is contribution from higher partial waves, which may not be negligible for finite energy collisions. Now here I'm showing the scaled three-body recombination rate for positive scatter lengths for 2 cesium-1 lithium atom for different partial waves. As you can see, in lowest partial wave, the recombination rate shows the log periodic Efimov features as minimums. However, the contribution from higher partial waves are highly non-negligible. And even if we increase the scatter length such that the finite energy Efimov feature in lowest partial wave extends to lower temperature or lower collisional energy, the contribution from the higher partial wave also extends to lower energy. So in general, only the first Efimov feature can be partially resolved in the total three-body recombination rate. Now, one possibility to get around of this problem is by looking at the angular differential distribution of the rates, which still needs some further study. However, for negative scatter lengths, situation is completely different. If you remember, as I have mentioned, that three-body recombination for negative scatter lengths can only happen at small hyperradius, where three particles are close together so that they can go to the deeply bound atom molecule channels. Now, in this case, because in the Efimov region, the hyperspherical potential for the higher partial waves are highly repulsive, and turns out the three-body recombination rate in the higher partial waves are strongly suppressed by this factor, where the exponent in this here is larger than 1. And because in the energy range we're interested, this variable here is much smaller than 1, so that which gives a strong suppression in the three-body recombination rate from the higher partial waves. So in this case, for observing finite energy Efimov features in thermal gases, the best scenario is still to go to negative scatter lengths. So this basically concludes my talk, and I would like to give a summary and some outlook. In summary, the exotic Efimov states also shows universal features beyond the ultra-cold regime. The finite energy Efimov features I have just shown have connection to the zero energy Efimov features and can be used to count the number of Efimov states in the system without changing the interaction. Finally, the higher partial wave contributions are significant for positive scatter lengths, but are negligible for negative scatter lengths, and can be used, which do not cause problem for observing Efimov features in this case. Now, there could be some interesting future study along this direction. Now, first, it is possible to analyze the nuclear scattering data accumulated in the past decades to try to find features of the Efimov states at finite energy. Now, another interesting thing is to look at the chaotic motions, because part of the three-body scattering in the finite energy three-body Efimov physics, Efimov features, stays in the region where three particles are finite region and have finite energy region and have a classical behavior, so that we would expect some chaotic behavior in the three-body scattering wave function. The question here is that will that kind of chaotic behavior, if any, can be coupled to the Efimov states and bring some chaotic behavior to the Efimov states? So with this, I want to thank the following people in this work. First, Jose Dinkau, who I worked together while we were with Brad Esri, who firstly found out the Efimov features. And my PhD supervisor, Brad Esri at Kansas State University, who guided me through this whole study. Also, I would like to thank Christoph Nargol from Innsbruck, who gives a lot of insight and suggestions for observing the finite energy Efimov features in experiments. Finally, I would like to thank my previous postdoc advisor, Chris Green, with whom we had a lot of insightful discussion about Efimov physics in general, and also the Efimov, observing Efimov features at finite energy. So with this, I would like to stop and thank you for your attention.
We're talking about this region of the potentials at the hyperspherical radius close to scattering band. You said that here you introduced some simple model of this combination. So how is it done?
Oh,
is it somehow
there are two ways.
Some parameters, or how is it done?
Yeah. So there are actually two practical ways to model the coupling in this region. The way I use it, just use a step function, and I can take the limit when the step function.
You mean you connect them like that? Or what?
Oh, step function it's finite here and 0 in other regions. Sorry. So then later I can take the limit to make this region to go 0, but with finite integral for the coupling. But it doesn't affect the final result. It just makes this result a little simpler and more easy to read.
But does it introduce some parameters into formulas or no?
It's true, yeah. The parameter is the integral actually of this coupling. So yeah, that's the C, yeah.
But the scaling is the same.
Exactly, yeah.
There's I think it's a very interesting effect here with going to finite momentum. And I think there's actually one application where, this is maybe more of a comment than a question, but there's one application where people have not looked so much into it, which is finite density degeneracy. So if you think about these three component gases that Salem had in his experiments and the experiments in Japan, they're actually not so far in terms of density. The energy scale of the Fermi energy is not so far from the binding energy of the Efimov states that they're seeing. So it's comparable. Most of the experiments were done at rather low density, so then of course it doesn't matter. But some of them were actually close, if you do these estimates. Now, if you look at that system, that means that you have a finite energy in the system because there is this Fermi energy, right? So
Yeah.
that means that something like what you're doing is actually perfect for seeing what the feature is if you take this degeneracy into account. Of course, now I'm talking about zero temperature, so there's another thing about temperature.
That's right, yeah. Yeah, thanks for pointing this out. Yeah, that's very relevant, I think.
I can point you to a paper that we wrote.
Yeah, thank you, yeah.
I just want to make sure I understand, right? So these results for recombination are on this slide here. Do they agree with the results by Petrov and Hammer and Bratman and all these other people who derived these in the early 2000s?
Oh, they actually didn't study. The energy range we study is different. So the energy range we are interested in is much higher than the energy range they are interested in.
So you want to do K of order 1 over R naught?
That's right. Yeah, a little. The thing is that their temperature or energy is still kind of comparable or a little less than the threshold energy or the energy of Efimov state.
Order 1 over MA squared.
That's right. In our case, our criterion for this kind of Efimov behavior exist in the regime where the energy is much higher than that. Otherwise, because that's what you see. Yeah. So it's a little slow. So actually, what they have seen is this smooth out of the features, or what they study is smooth out of these features at finite energy beyond this threshold. What happens is that if you go much higher than this, instead of seeing this kind of smooth out, you will see some new features.
You extend your calculation to consider the free particle in the lattice size, and then if you change the confinement, then you think for dew point energy in order to scan over large range. In that case, you also expect that this.
Yeah, in principle, yes. For at least for 3 identical bosons, it won't be difficult. For heteronuclear systems, because central mass motion is not necessarily coupled, does not separate from the relative motion in 3 particles. In that case, maybe some approximation can be made, but I think that's also possible.
Non-related question. Also, people are not talking about free body law, right enrichment, and universe. If you also change the scaling energy, you also expect to see some kind of additional features.
Yeah. Yes. In that case, because it goes to the unitarity limit, actually, I think that goes to the case where the scattering is negative. The recombination path, you cannot, because there's zero binding energy for the Feshbach molecule, you cannot recombine into that state anymore. What you can recombine is into the deeply bound atom molecule channels that gives loss. So that corresponds to negative scattering case.
Maybe you have answered that already. I just want to make sure. So are there now active theory or powerful about the temperature dependence of all this recombination rate? I would have thought that at sufficient high energy, then you would have to look into some of this chaotic motion. So I was wondering what's the current situation for understanding the temperature dependence of these rates?
As far as I know, there hasn't been any studies, a general study for finite temperature or finite energy dependence in 3-body recombination. As I have shown in one of the slides, for the higher partial contributions to 3-body recombination rate at positive scattering lengths, you can see that without going very high temperature or very high scattering energy, you have like a partial wave contribution up to 100, angular momentum of 100. In general, you have to add up all the contributions from 0 to that many angular momentum to get the full recombination rate. So, although I would expect the 3-body recombination rate in that case should turn out to be universal, but as far as I know, nobody really carried out calculation including that many partial waves. The thing is that for chaotic behavior, when you go to that high energy, it's more in the chaotic behavior is more in the elastic scattering of 3 particles. That's a connection where you make with the classical mechanics. Now, seems like so far we haven't seen so many signatures of the chaotic behavior in 3-body recombination. However, because of the contribution of so many higher partial waves for positive scattering lengths in 3-body recombination rate, it is possible a signature or some hint for the startup of chaotic behavior at some point.